All right, chemistry class, good morning. Welcome to our third lesson about light and quantized energy. Remember, the first video was about the wave nature of light. Second video was about the particle nature of light. And this is about the dual nature of light. Okay, so it ties it all together, hopefully. Okay, and at the end I'll assign some questions and I'll send you a photo of the board. So, Leilani, so you can see it a little bit better. So this is a very confusing concept, and I'm going to do my best to explain it. It's just hard to understand how light can be two things at once. But Einstein tried to explain it. Okay, so he was the one in 1905. Albert Einstein proposed that light has a dual nature. Okay, so it was his idea. Okay, and here's some ways to think of it. So you think of it as a beam of light has particle and wave-like properties. It has both. Okay, think of it as a beam of bundles of energy called photons. So you have the beam of light, and in the beam are bundles of energy. So that way the beam is like the wave theory, and the bundles of energy are like the particle theory. Okay? So you think of it as a beam of bundles of energy called photons. Okay, so what is a photon? Well, a photon is a massless particle that carries a quantum of energy. Okay, so a photon has no mass, but it carries energy, which is confusing. But that's the definition of a photon, okay? So photons have no mass, but they carry energy. And photons are what make up the dual nature of light. A photon is what's in the beam of light. The bundles of energy in the beam of light are called photons. Okay? So, a beam of light with bundles of energy called photons, and the photons have no mass, but they carry a quantum of energy. Okay, so then what Einstein did with this information, he took the equation that, who came up? Planck's equation from the last. He took Planck's equation, and remember in Planck's equation, it was energy of a quantum equals h times v. Okay, but now it's energy of a photon, because he says, oh, it's photons. Photons are what we want to find the energy of because of the dual nature of light. We know the photon is the packet of energy that we're looking for. Okay, so you have energy of a photon is energy, okay, h is still Planck's constant, and the funny v is still frequency, okay. And remember, Planck's constant is 6.626 times 10 to the minus 34th joules times seconds, okay. So the only thing that's different is instead of energy of a quantum here, remember the last video where I talked about this? It's energy of a photon, okay. And we'll do a sample problem with that in a second, okay. But, so then Einstein also proposed that the energy of a photon must have a certain threshold value to cause the ejection of a photoelectron from the surface of the metal. That's a big mouthful, but remember, from the photoelectric effect, they hypothesized before they knew about the particle nature of light. They were like, oh, no matter what type of light shines on a metal, if it shines on there long enough, it will eject a photoelectron. But that's not true, right? We learned that wasn't true. So that's because so it means So even small numbers of photons with energy above the threshold will cause the photoelectron effect. So what that means is if the light doesn't look very bright or isn't very strong, as long as it's at a certain frequency, it will hit the metal and the metal will eject the photoelectron. Like in remember the last video where I talked about this, right? So there can be not very many photons, but as long as the photons are above a certain frequency, they'll hit and eject photoelectrons, which is it's contrary to wave theory. So that's why we had to come up with the dual nature theory. So again, Einstein said that the energy of a photon must have a certain threshold value. A certain threshold value is like, it has a certain amount of energy. It must have a certain amount of energy to cause the ejection of a photoelectron from the surface of the metal. So even though there may not be very many photons coming in, hitting it, that doesn't mean that they won't eject a photoelectron. Okay, they might just come in, but they're at a certain frequency and there's not very many of them. They can still eject the photoelectron. Okay, so that was explained. So now Einstein's dual nature theory of light is starting to explain these phenomena that we couldn't explain using just the wave theory, just the particle theory. His dual nature theory is explaining things better. That's how we know it's right. Okay? So it means, again, small numbers of photons with energy above the threshold, energy above a certain level, will cause the photoelectric effect. So even though there's not very many of them, if they're at a certain frequency, they come in and they hit the metal and they'll eject the photoelectron. Anyway, okay? Now let's look at this sample problem, okay? Alright, my calculator. Everyone get their calculator? All two of you? Okay, good. Hope you got the calculator. Alright, so we'll start off. So basically this is I wrote the problem up here. It's problem 2 from EduSystem. Look at EduSystem. EduSystem has more words. If you like words better to explain things. I'm just trying to hit the big important points in these videos. You know what I'm saying. So, problem 2, calculate the energy of a photon. Okay, I only wrote it down because I want you guys to know which problem it is, so you don't get confused. But this is not very important stuff, like the problem itself. Every object gets its color by reflecting a certain portion of incident light. Okay, nice. The color is determined by the wavelength of the reflected photons, thus by their energy. What is the energy of a photon from the violet portion of the sun's light if it has a frequency of 7.230 times 10 to the 14th, 1 over seconds, which is a hertz. Remember, seconds to the -1, 1 over seconds. Okay? So, the question is, what is the energy of a photon from the violet portion of the sun's light if it has a frequency of 7.23 times 10 to the 14th? So what do we know? Well, remember, we know Planck's constant. Remember, we always know Planck's constant. 6.626 times 10 to the -34 joules times seconds. We know that. And they gave us the frequency. Remember, the frequency is right here. Frequency of the portion of violet light from the sun that we want to figure out the energy of is 7.230 times 10 to the 14th. 1 over seconds, okay? I'm going to get the desk here so I can write things down. Okay, so what do we do? Right, so we have H and we have V. What are we trying to find? Energy of a photon, okay? So we're trying to find. So from there, we take 6.626 times 10 to the -34th times 7.230 times 10 to the 14th. And remember, we put that in parentheses so your calculator could handle it. You multiply them, and what do you get? You get, oh, man, this marker, every time I try to do these videos, it gets cold. It doesn't work. Okay, so it's 4.790598 times 10 to the -19th. And what's our units? What's our units? Well, it is 1 over seconds, and if you do units, so this is joules times second over 1 right here, right? And this is 1 over seconds. Your seconds cancel out, so you're left with joules. Your units are joules. But remember, we have to do significant figures. So since these are all out to 3 sig figs, 2 sig figs, then energy of a photon, E photon, equals 4.791 times 10 to the -19th joules. Box worthy. Okay? So that's how you do that. I think there's a problem like this on the review questions. So I want you guys to do the review questions 8 through 14 and then email them to me, okay? And next week I'll make the video answering the questions. So this is going to be your last assignment. I'm going to make you some more videos next week to explain stuff. But since school is done on the 8th of May, I'm not going to assign you new homework next week. I'm just going to give you some videos to watch just to learn some things because I think we haven't talked about enough stuff. I wish we could have talked about way more things in this class. I feel like I came in late and you guys weren't very far and we just didn't talk about enough stuff. There's so much chemistry you don't know. I mean, so much chemistry I don't know either. You know, no one knows all the chemistry, but we're always learning. So, but anyway, so try this practice problem and do problems 8 through 14 from the review questions, okay, on this lesson. The lesson is light and quantized energy, okay? So watch all the videos, do the questions, email them to me, or if you don't, or you can wait to email them until you see my video I post next week where I answer the questions, okay? No rush, okay? I just need it, yeah, eventually, okay? So, watch the videos, do the questions, 8 through 14. If you have any questions, let me know. Leilani, thanks for asking those questions. That was really good. I feel like I'm glad you guys are doing your best to learn online. And, yeah. All right. see you guys next week when I make the video to answer these questions, and maybe some other bonus videos to teach you some more stuff. Okay, nos vemos.